right, well, welcome back, and we're going to talk about in today's lesson is the chi-square test for homogeneity. All right, and key concepts you need to understand is that, like a chi-square test, we are going to talk about uh, the values that are going to be categorical. Okay, so whenever you're talking about values when you have categories, all right, categories, that is going to be used for a chi-square test. Now, unlike Goff, we have one sample and one variable, all right, which are broken down into different categories that we have here, all right, and usually those are proportions. But for homogeneity is that we actually are dealing with experiments, okay, experiments. And that's a key indicator that when you have experiments that are broken down into categories, all right, and we're looking to find out if two samples have something in common. This is one variable, which we can say different categories right here. All right, so we have two samples, one variable, different categories with that variable, and we're trying to figure out, is there any correlation? All right, are they the same? Is the claim possibly the same? All right, is there any difference between them? And so what we do here then is once again, we start with the hypothesis, okay, in our state part, and we say there is no difference in the categorical variable distribution from population to population. So there is no difference. However, our alternate hypothesis is there is a difference, okay? There is a difference in the category of variable distribution from one population to another. Now, there's a different way of finding expected counts as well. So when you're doing this expected counts and degrees of freedom, okay, we find expected counts by going row total times column total divided by table total, all right? And that's how we're going to find expected counts. And we'll go through that in just a little bit. And then our degrees of freedom are rows minus 1 and columns times columns minus 1. And that's how we figure out degrees of freedom. Now, this will all make sense in a little bit when we do an example. All right, so here is our example for today. All right. Thanks to StatsMedic for helping us with this and with their information. That's where we're getting this from. And so for a class project, Abby and Maya wanted to know if the gender of an interviewer could affect the response to a survey question. The subjects in the experiment, so once again, we have an experiment here, where 100 males, okay, 100 males from their school, half the males were randomly assigned to be asked, okay, so we get 100 males, and now they're random assignment, okay? Random assignment is happening, okay? So we asked, would you vote for a female president by a female interviewer? Okay. So the other half of males were asked the same question by a male interviewer. And the table shows the results below, okay? And you can see that right here. Now, going through this, okay, we can see that we have different categories. We have yes, no, and maybe, all right, in response to the question. And we have interviewer, which is male or female, male or female. And so we want to state the appropriate null and alternative hypothesis. So in this case, we have a hypothesis, a null hypothesis, which states that that we're looking for is other half. And so we were trying to figure out if the gender of an interview could affect the response to a survey. So basically what I'm going to say is that the gender of the interviewer, all right, has no effect on the response to the survey question. All right. And so that is what we are basically saying. So we're basically saying that it has no effect. So we're saying that there is no effect that's going to take place. However, our alternate hypothesis is that the gender, all right, of the interviewer has an effect on the response to the survey question, all right? And that is what we are looking for. Okay, so when we talk about this, so we have an experiment. There are two different samples, okay, two different samples. A sample of where they're interviewed by sample number one, so I'll just say it right here, sample number one, where it's males, all right, is being interviewed by males. And then we have another sample, sample number two, all right, which males are being interviewed by females. And these are the indicator responses that they have, okay? So this is our one variable, okay? The variable is the response. And it has three different categories, okay? So there's three categories in this response. For our sample, we have basically two samples, and we're going to have that right there. Now, the next thing is we want to show the calculation for the expected count of count in the male yes cell, okay? So male yes cell, all right? So this expected count right here, then provide complete table of the expected count. So for the first one, this is how we do it. Is if you recall, we're going to take our, all right, row times our column divided by the, all right, total amount. So in this case, we're going to take 69, all right, times 50, and we're going to divide this by 100, okay, 100. Okay, so this is going to be the male, all right, slash yes, all right, cell expected value. And so you can go on your calculator and you can figure this out. And when you punch that into your calculator, you should get a value of 34.5. And so that is the expected amount of people, all right, for males being yes. Now we can write out our complete table. Okay, so if we go over here and say this is males, all right, this is females, oops, female, all right, and these are our interviewers, and we'll say yes, all right, no, and we'll have right here is maybe, and I'll bring this down a little bit. And what you notice when you fill this out, so this is going to be 34.5, is that the expected count, if there is no difference, there's no difference, we'll just have this, all right, times this for this one, all right? So this 69 times 50 divided by 100, that would be the same thing. All right, so the expected value, whether you had male or female, all right, would be the same. It would be 34.5 and 34.5. Now over here in the no column, we would say for the no, all right, male no. Okay, if we want to find that out, we would take 11, because that's our row total value, times our 50 divided by 100. Okay, you can put that in your calculator real quick, and what you get is going to be 5.5. Now you notice that that expected count for males and no, and female being interviewed by a female and no will be the same, because there is, once again, we're assuming there is no difference. That gender has no difference in the response that we have. Then finally go to maybe, and all right, so male and maybe, and I'm just going to write these down. We only need to know this one. That's all I ask us to do, but I'm overachiever, and so we're going to have 20 times 50, okay, 20 times 50. And so for each one of these, and just so you know, for this one, because it is 50, so 69 times 50, these happen to be the same, and that's why these values are going to be the same right here, okay? Because we know that there is no difference between them, because they have the same amount in each one. And so right here, we divide this by 100, and so we have 20, all right, times 50, all right, divided by 100, and we have 10, okay? So 10. And because these counts are the same, and we are assuming that we don't have any difference, and so we have our expected values, which are located here. Okay. Now, from this point on, is now we need to calculate the value of the chi-square test statistic. Okay, and we're going to use our calculators for this, and I'm going to show you first how we can set this up. So over here, okay, is we're going to find our chi-square statistic. I'm just going to keep this up here. And what we do is we take our observed value, just like we did before. So 30 minus 34.5 squared divided by our expected value, which is 34.5. And we need to do that for every single one of our values. So if I want to do the next one, I could say 39, all right, minus 34.5 squared divided by 34.5. And I would keep on going, dot, 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 and all the way to the last one. I'll just go to the last one right here. So if we go our observed value of 8 minus 10 squared divided by 10 right here, that will give us all of our values. Now, that would then be used to help us figure this out. So what we're going to do here is if you take out your calculator, we can actually import all this data, all right, into matrices, okay? And this is what you want to do. So if you go to second matrix, all right, and we're going to go to edit, and we're going to matrix A. Matrix A is going to be my observed values. So my observed values right here, and I just punched those in here. So I have a 3 by 2 matrix. I have 30, 39, 8, 3, 12, and 8. Now from here, I'm going to do the same thing. Go to second matrix. Now I'm going to go into second matrix. Oops, there we go. All right, there's some good secant lines right there. All right, but we're going to go down to B. Now from here, we're going to put in our expected values. And so we see our expected values right there are going to be 34.5, 34.5, 5.5, 5.5, and 10 and 10 right there. Now, we now go to our stat, and now we're going to do a test. Now, before we did a chi-square test for goodness of fit, well, this is not goodness of fit because we have 2 samples, 1 variable, and this is just going to be a chi-square test. So we're going to go down or go up or press C, or whatever you want to do. Press enter. Now this is what you have. So you need to put this in the matrix C. So we have matrix A. Now if you're not sure how to get matrix A, you just go second matrix and you just put A right there and it'll pop in here. All right, then we go down to B, go to the same thing, second matrix. And then you can go down to B and then we'll pop in there, if you're familiar with that. And then it's going to take all these values and now we're going to, all right, calculate that. Bada bing, bada boom. I'll take those values right there, and we can identify right here all this information, which is very, very nice, and we can use this to surmise some other things. So what it has right here, it gives us our chi-square value, it gives us our p-value, and also our degrees of freedom, which if you recall, what we do is we take our rows, all right, total number of rows, so be 2 minus 1, all right, so rows minus 1, and then we multiply that by our columns, all right, minus 1. And so this would be 3 minus 1, which would equal 2. Okay, so that's how we figure out our degrees of freedom if you weren't sure. Our p-value right there, we can do a table, or if we recall, this is still a chi-squared value. All right, and we find our chi-square value is going to be right about there, which is going to be equal to 4.24. This is 0, as we know, and so what we found out is this, all right, p-value is actually the probability that we get a chi-square value, which is going to be greater than or equal to what we found, 4.247. And that would equal 0.119, or 20 if you want to round it. And we have that there. So finding how to calculate the value of chi-square test significance, I also added onto this problem of how to find the p-value and also degrees of freedom. And then we can do some inferencing, all right, if we wanted to, well. So that's what we got. So this is how we use the chi-squared test for homogeneity. It is used when we have categorical data, all right, usually when we have experiments, all right, we have 2 samples with 1 variable. Okay, 1 variable. All right. Well, I hope this helps you out, and good luck and God bless in the rest of your problems.